Welcome back. Now that we've learned what stable glasses are, and that glasses can be made of small organic molecules, it would be natural to wonder what affects the stability of vapor-deposited molecular glasses. Once more, we will refer to the volume versus temperature plot, and this is where our supercooled liquid and liquid quenched glass lies, along with the glass transition temperature, Tg. For the starters, we notice that the state function is plotted as a function of temperature, so maybe glass stability has something to do with temperature here. And since the temperature involved in physical vapor deposition is the substrate temperature, you would be right if you think that deposition temperature affects the glass stability. I guess the next question is, what exactly is the influence? I would like to point out that we know the supercooled liquid is a metastable state, meta, in the sense that if you throw a crystal seed into the system, the whole liquid crystallizes, but otherwise it is really a stable state, as in, it is at equilibrium, just like an ordinary liquid. Glasses, on the other hand, are non-equilibrium states, and have larger volume than supercooled liquid. Consider what happens if we set the deposition substrate to a temperature above Tg. Well, yes, glasses don't exist at this temperature, so in the vapor deposition process, the ensemble of surface molecules still rearrange, but become nothing more than just supercooled liquid. On the other side, if we look at a temperature below Tg, during vapor deposition, the surface molecules still want to achieve perfect equilibrium. They don't always get there, but still, they have already bypassed the liquid quenched glassy state, and thus constituted stable glass. Just a bit of recap. The volumetric difference between liquid quenched glass and the vapor deposited glass tells us how stable the latter is. We can further divide the x-axis into near Tg, and far from Tg. On the higher temperature side, the surface molecules have higher mobility to rearrange, but there isn't really a big gap between the energy of liquid quenched glass and the extrapolated supercooled liquid, so here is the density increase of vapor deposited glass compared to liquid quenched glass. On the lower temperature side, the energy gap becomes larger, but the surface molecules don't move fast enough to rearrange into better configurations, and we shall draw the density change here. In overall, we are seeing an interplay between thermodynamics and kinetics. On the near Tg part, the limiting factor of density increase is thermodynamics, while on the far from Tg part, the limiting factor is kinetics. If we connect the data points of density increase along the deposition temperature, this is what we would observe. The largest density increase occurs somewhere between 0.80 to 0.85 times Tg. I'll illustrate this magical number with some experimental data. And here we have experimental results from a paper published by our group. As the curves suggest, it is a common trend that the density of vapor-deposited glasses of these molecules all depend on the deposition temperature. There is also the phenomenon that the highest density increase is observed between 0.80 to 0.85 Tg, and this relative temperature range seems to be universal for the vast majority of glass-forming molecules, regardless of how high or low their Tgs are. Let's go back to the discussion of the factors that play a role in determining the stability of vapor-deposited glasses. This is another paper in the PVD glass community that reports the enthalpy of vapor-deposited glasses of various thicknesses. As you can see, as thickness decreases from thick to thin, the enthalpy decreases. Enthalpy here works pretty much the same way as volume. The lower it is, the more stable a glass is. So we know that film thickness also affects the stability of PVD glass. The questions are again, why, and how? Well, actually, when I mentioned mobility before this, I may have overemphasized the mobility of surface molecules. The truth is, all molecules in the glass move around, and we're not just talking about their rotations or vibrations, we are in fact talking about their translations within the film. Their moving around is exactly why liquid quenched glasses can have physical aging to become more densely packed structures. With that in mind, we shall look at literature data that tells us how mobile the molecules at different positions in a film are. On the y-axis, a shorter relaxation time means a faster motion. On the left side we have molecules attached to the substrate that are pretty much stationary, and on the right side we have molecules near the surface which have way more freedom than those sandwiched in the middle. Let's divide a film into two parts based on mobility. When we look at a thick film, it has a large bulk portion, and a small surface portion, corresponding to low and high mobility, respectively. As film thickness is decreased to below 100 nanometers, or what we describe as thin films, we have a thinner bulk portion, whereas the near-surface portion becomes more dominant in the film. Obviously, if the overall dynamics of the film is enhanced, we would expect to see some changes in the behavior of the vapor-deposited glass. For example, in this work, we notice that when the film thickness of a vapor-deposited glass was decreased below 30 nanometers, the apparent activation energy of rearrangement was observed to drop sharply. This means that packing rearrangements in thin films are faster, which intuitively lead us to think that more stable states will be reached. So much for background knowledge. Let's look at some of the research work I've done in the past 3 years. Please let me introduce myself a little. This is Yi Jin, a 5th-year PhD candidate in the Fakhraai group. My work is centered around stable glasses. If you have even the slightest interest in knowing more about my work, please don't hesitate to reach me through email. By the way, I'm most certainly a cat person. This is my workspace avatar, and these cute little creatures here are my Angelica, Eliza and Peggy back home. The remaining of this video is about the experimental techniques we use in our lab. I'm only going to talk about instruments that are already well established here, so if that doesn't satisfy you, please check out the next video. I have been relying heavily on the term, density change, to quantify the stability of vapor-deposited glasses in my research. Suppose we have a vapor-deposited glass here. To compare its density difference with liquid-quenched glass, we have to know its volume. Thankfully, there is an experimental technique called spectroscopic ellipsometry that made me different from 19th century scientists. Instead of measuring the volume of a large chunk of solid, here's what we can do. Assuming the film area stays constant, all I need to know is how much the film thickness changes. Spectroscopic ellipsometry is sensitive to film thickness change as little as 0.1 nanometers. The principle of this method goes as follows. There is a polarized light interacting with the optical medium, in this case, the transparent glassy film. A portion of the light gets reflected, while another portion gets refracted. Ellipsometry measures the reflectance ratio, which is then fit to models. From there we obtain the values of optical constants such as thickness, or refractive index of the glass film. There is quite a lot more information in a glass film than meets the eye, both literally and figuratively. I'll give another example, the surface morphology. It can be smooth or rough, have ridges or valleys, bumps or holes, but all of that is invisible to the naked human eyes, sometimes even optical microscopes. This is when we need to employ a technique called atomic force microscopy, or AFM. There is a tip that scans across a surface from point A to point B, and detects the amount of force the tip feels throughout its trajectory. As you may have guessed, the atomic force is a function of the distance between the tip and the surface. So working from force to distance, the distance as a function of position can be obtained, thus the morphology of a film. Let me draw your attention to the film once more, this time from macroscopic properties to a microscopic property. We know that in crystals, molecules take on a specific orientation. In glasses, the long-range order is missing, but certain orientations can still be preferred by molecules over others. If there exists such a preference, the glassy material is considered anisotropic. Otherwise, if the orientation of all molecules are perfectly random, the material is isotropic. If molecules are aligned along a particular direction, the macroscopic properties in different directions can also be different. For example, if there is a difference between refractive indices in different directions, there is a high chance that the glass is anisotropic. Ellipsometry is one of the many methods that provides this information, but more than often, we also employ techniques such as X-ray scattering to get a better idea of the anisotropy in glass films. There are a lot more experimental techniques that we frequently use, in terms of preparation and characterization of glasses, but I don't have the luxury to cover all of those in this video. On many occasions, we would also like to dynamically observe how glass properties change with temperature. That involves heating and cooling of a glass film in situ on the experimental setup. So far, we have been able to accomplish this on major lab instruments, but since many of our temperature setups are manually designed, I envision a future where pretty much any instrument in our lab can accommodate temperature settings. Guys, if you did enjoy this video, make sure to leave it a like, and if you're new to the channel, make sure to subscribe, because videos will be incoming. Thank you for your support, and I'll see you in the next one.